Hi everyone, welcome back to another lecture in mechanics. So we've been talking about objects near the surface of the earth and how they move, such as baseballs, basketballs, people jumping, right? Cars driving down the road. So all of these objects move in a straight line, right? They're going either up or down, left or right. And so what we're going to do now is we need to address the other moment, what is the word I'm looking for? Degree of freedom, not moment of inertia, which we will talk about. Another degree of freedom, right? Another range of motion, and that's rotation. So we're going to look how and learn how to describe the rotation of rigid bodies, okay? And we're going to figure out how that connects with Newton's laws. And we'll define some new terms. And we're basically going to have a whole nother language here. The good part is that the skills that you need to solve these problems are going to be identical to the skills that you used to solve projectile motion problems and Newton's laws problems. So really important objects to us are rotating objects, such as the propellers in an airplane or inside of the jet turbine on the big airplanes, right? Those rotating fans, blades keep us afloat, so we need to fully understand their motion. We also have doors. Doors are pretty important, right? When you open a door, you are not moving that door linearly. You are swinging all parts of that door open, and all parts of that door are rotating. And then, of course, the fan, right? Everyone's favorite object in the summer heat in Florida, the fan, another rotating object. So we need to define the motion of these rotating objects. The first thing we're going to do is, well, what about the coordinate system? Where is the location of this rotating object? We're not going to use X, Y because X, Y is, kind of like a linear type of arena, right? When you have an XY coordinate system, your object can, move. So when we're dealing with rotational motion, we're going to need a coordinate system, and the coordinate system is going to be an XY plane. But now we're going to look at how the object moves in the XY coordinate when it's rotating, okay? So this is an example of a rotating object. This example is getting a little bit outdated as time goes on because now our speedometers are no longer analog, where you have a dial that is rotating about an axis telling you how fast you're going, right? 0 miles per hour, usually 50 or 60 is up here, and over here is like 80, 90, right? And then 110 miles an hour, right? So a lot of you probably drive cars like that, but nowadays it's replaced by a screen. But imagine, if you will, an object that is rotating about a particular axis in the XY plane. It's going to be measured by, its location is going to be measured by the angle, right? The angle that the object makes with the x-axis. So instead of specifically using X or Y now to describe the motion of a rotating object, we're going to use angle, okay? Theta as our X or Y, okay? Theta, though, is related to X and Y, right? Through the Pythagorean theorem. So, but the idea here is that we're going to use theta is going to be replacing our X or our Y. That's the idea. So let's talk about angles, okay? Well, there's two different units for angles. Well, there's a couple more, but the ones that we're going to be using are degree and radians. So you probably already aware that 1 radian is about 57.3 degrees. And then the conversion factor is 360 over 2 pi, or obviously 180 over pi works as well. That's how you convert between radians and degrees. So you may be wondering, what the heck is a radian, right? What is a radian? A radian is a ratio of two numbers, okay? A radian is a ratio of the arc length of a curved surface or a curved, piece of a circle, right? That's this length right here. And the radian is a ratio of that length to this length, which is the radius of the circle, okay? And so 1 radian is going to be when S equals R. Right? So because 1 equals S divided by R, right? 1 radian is S over R. So that means S must be equal to R. So 1 radian, when something has an angle sweep of 1 radian, what that is saying is that the arc length and the radius are equal, okay? So angular velocity is obviously going to be the rate of change of the angle with respect to time. And this is going to be an average quantity. So whenever we use average velocity, it's when we are finding the velocity from like 2 data points, okay? And that's the same for angular velocity. So we're using 2 data points to find the velocity. Position 1, or I should say position 2 minus position 1 over the time it takes to go from position 2 to position 1, right? So, or 1 to 2, I should say. And so our average angular velocity is simply that delta theta over delta t, right? In the same way that our regular average velocity, our linear one, was x positions subtracted divided by delta t, right? And so now we have this extra subscript here, z, in our angular velocity. And what that tells us is that the axis of rotation is the z-axis. And that's just a convention that we use. Typically, when you're looking at a problem for the first time and it's a rotational problem, you'll want your object to be moving around in the xy plane, which makes the rotation axis the positive, or the z-axis. We'll talk about positives and negatives coming up very soon. There we go. So, right, what's a positive velocity and what's a negative velocity in angular velocity terms? So another convention is that we choose increasing angle, so positives or increasing angles, to be counterclockwise, okay? The reason for that is if you take your fingers of your right hand and you follow that grayed arrow right here with the fingers of your right hand, trace it around, take a look at where your thumb is pointing. When you do that, your thumb is pointing into the page, and technically that's going to be the negative z-axis, right? Now, put your fingers of your right hand and curl them in the counterclockwise direction. You'll notice that your thumb is pointing out of the page, and that's going to be the positive z-axis, right? According to the xy that we have right here. Positive z should come out of the page towards us, okay? For both pictures. So that makes this angular velocity have a positive or negative sense depending on which direction the object is turning. And so the instantaneous velocity equation follows pretty closely to what we've already learned in the translational or linear terms, right? It's going to be that delta theta over delta t taken as the limit as that time becomes smaller and smaller. So it's just a time derivative of theta, okay? Just the same way as that it's either dx dt or dy dt for velocity. So again, the subscript z refers to a rotation about the z-axis, okay? Meaning we're tracking the object's motion in the xy. So in this example, I'm going to skip this one for this video, but you can do it on your own. It's basically an example where you become comfortable with the language, and here you're given an angular position of an object as a function of time, okay? Angular position as a function of time, and then you're going to calculate some values based on this function right here. So it's a good one to get used to the language of what it means to find the average angular velocity, what it means to find the instantaneous velocity, okay? I think it's a good one to do, but I'm going to skip for this video. We're going to do some more complicated ones. So, we talk about obviously the rotation, the positive rotation would be counterclockwise and the negative rotation would be clockwise, and one's positive and one's negative. So take out your right hand, and now you're going to learn the first of many right hand rules, okay? And so the right hand is important because this is kind of how we all are on the same playing field. We all are agreeing to how things should be moving and what the positive sense means. So that thumb that points, along the z-axis, that thumb is going to be the vector, okay? So angular velocity is a vector, right? And it can be a little bit strange because you're used to a vector pointing kind of in the direction of motion, right? So when you think of a little ant and he's, walking along to the right, you think that his velocity vector is going to be to the right because, right, he's moving to the right. Velocity vector is the right. Well, angular velocity vector doesn't behave the same way. So if this ant is on like a hamster wheel, and it's rotating around. So I'll draw this curly arrow here. This is not a vector, right? Vectors can't be curved. This is just a schematic arrow, kind of like this one, right? Indicating the direction of the rotation. This is just a visual aid, not a vector. So the question is, if this ant is now rotating in a circle, what is the direction of its angular velocity vector? Well, it's not the tangent, right? That's going to be the linear velocity vector. It's not any of these. These are all linear. What it is your thumb is going to point into the page because the fingers of your right hand are going to follow that curved arrow, and your thumb is going to be pointing into the page. So the angular velocity vector of the ant is actually into the page. Okay, into the page is represented by an X. Okay, an X into the page, right? So a 3D or, a 3D representation, or I should say a 2D representation of a 3D vector, right? A vector pointing into the page has a cross. A vector pointing out of the page is represented as a dot. Okay, and so you'll need to get used to that imagery for this chapter and the next one. So angular velocity is a vector, okay? Moral of the story is the vector does not point in that rotational direction. It points perpendicular to that rotational direction. Here's another view. Okay, so now here we've kind of rotated the picture, right? This picture here is rotated. Well, really, actually, it's probably this one right here, right? Because our velocity vector was pointing in the negative z direction. So this is the picture this is the rotating picture, right? It's rotated. The z is pointing now in the up-down direction. And you'll see this representation a lot in your math book, right? I don't know if you ever, you're taking calc. A lot of you just started calc right now. So if you look at your calculus textbook, you'll notice something, it's kind of interesting. The calc book likes to put the z-axis, kind of in the north-south, up and down, whereas in this book, you'll see a lot of times the xy like this and the z coming out like that. So I want you to just, be aware of that, right? That you're going to start where, things are getting a little bit more complex, not just in this class, but in all of your future classes coming up. You're going to be expected to be able to kind of look at pictures and be able to rotate them around, okay? And this is a perfect example of that. So let's move on now. Obviously, we hit position, we hit velocity. Now we are talking about acceleration, angular acceleration, okay? So, position vector, velocity vector, acceleration vector, right? They were all collinear, right? They all either pointed, to the right or to the left. but along the same line, right? Collinear. Well, all of the angular terms are a similar form, except they're not pointing in a line in the same direction as x, v, or a. They're pointing all along the z-axis, right? So now angular acceleration is also going to be a vector that points along the z-axis. Now the magnitude of that vector is given by the change in angular velocity divided by obviously the change in time, right? We know this. And the instantaneous version is simply the time derivative. So vector-wise, you have the same kind of collinearness, okay? And the same reasoning behind whether the acceleration and velocity vectors point in the same direction or not, okay? When they point in the same direction, you're speeding up, right? Linearly, but you're also speeding up rotationally. So if the angular velocity vector and the angular acceleration vector point in the same way, that rotation is speeding up and getting faster, rotating faster and faster. Now, if they're in opposite directions, the rotation must be slowing down, right? Because for the very same reason, when velocity and acceleration are pointing in opposite directions, you know it's a slowdown situation. So in this example, we're gonna it's gonna bounce off of that first one. It's gonna use that same functional form. So this one will be a DIY as well. And we'll get into some more difficult problems. Now this is one I do wanna slow down and look at. Okay, this is a great example of a test style question. So here you're given the acceleration and velocity, angular, obviously, with respect to time. And in this graph, we want to identify which intervals you have a speeding up rotation or a slowdown rotation, okay? And that's going to mean we're looking at the signs of those values and whether they are the same sign or opposite signs, right? So remember, same sign, you have a speed up. Whether they're both up or both down, right? Opposite signs, you have a slowdown. No matter if it's a velocity vector pointing up and an acceleration pointing down or vice versa, right? So let's take a look. Where do we have opposite signs and where do we have same signs? So I'm going to highlight where we have positive. So here we have positive A, alpha, I should say. And where do we have positive omega? Positive omega exists in this area. So wherever we have an overlap is where we have same sign. And we have a speed up. So that looks like it's going to be from 0 to 2 seconds, right? Where do we have an opposite sign situation? It's going to be right here. Right, between 2 and 4. Alpha and omega are in separate sides of the t-axis, right? And then, actually not greater than or equal to. That one is, but this one is not. There we go. And then our final interval, they're both having the same sign, right? This is negative and this is negative. So just keep that in mind, right? This is stuff. This is conceptual stuff from chapter 2 and 3, right? And it's coming up again, but in a slightly different, set of terminology, right? A rotational set of terminology. So let's talk about what we can do with this information, okay? We can now solve problems with constant angular acceleration, all right? If we assume, or if we're, have instances of constant angular acceleration, we can use the same tools that we use for straight line motion. Assuming a constant acceleration means that you know the velocity changes in the following way, right? You know that the velocity change is going to be linear. And if the velocity change is linear, that must mean that the position change is with a square of time, right? So when I said linear, I meant linear with time, and the position changes with the square of time. And then you have your other auxiliary relationships that can be developed based on combining those two equations, and that's these two right here, which you'll recognize. So in situations where you have constant angular acceleration, you can just use your toolbox of kinematics. That's what I want to work on with you, okay? And so in order to do this, you need to be really comfortable with the rotational motion, okay? So here's an object that rotates, and you probably barely know what this object is. It's a Blu-ray or a CD, okay? It's a disc, and this is how we used to own movies. Now you don't really own anything anymore. Interesting thought. So in this disc, we are given the angular velocity at a particular time. Okay, this disc is rotating, and its speed is 27.5 radians per second at its initial time that we start measuring. And what we know is that we have a constant angular acceleration, which is great. That means we can use our kinematic equation equivalence. So now we need to pick a place on this disk to monitor, right? A particle, if you will, or a location on this disk. And in this problem, we've just defined this entire line right here, okay? Just one line on the disk, and it's going to start rotating around, right? It's going to start moving around like this. And then obviously it's going to be at different angles at different times, right? So what we need to do is figure out what the angular velocity is at 0.3 seconds. And then finally, what angle does that line make with the z-axis at t equals 0.3 seconds? So I think what I would first start off with is writing down the information that you're given. And let's open this in a new. So let's review the information that we're given. We're given at t equals 0, omega, which I'll call omega naught, equals 27.5 radians per second. We know that the angular acceleration is constant and it's negative. And so we want to know what is omega at t equals 0.3 seconds. So we can grab our chart with all of our kinematic equations on it. And from there, you will remember one of the easiest ones, right? How the velocity changes with constant acceleration. It changes linearly. And this is the form. So if we want to know omega at 3.3 seconds, right? That's this value. We're going to need omega at 0 seconds. We're going to need alpha. And then we're going to need the time, obviously, which is the 0.3 seconds. So we'll plug everything in, solve for that unknown. Don't forget your negative here because your acceleration is negative. We can write in all our units. I would recommend to do that initially so that you can see the units cancel out appropriately, and it gives you that confidence and that intuition about problems if you just write the units out. And I am sometimes guilty of dropping units, especially when things get a little bit hairy, but in the beginning like this, you should put your units down. So we're going to have 27.5 radians per second minus 3, right? 3 radians per second, because once I multiply the seconds, I'm going to drop one of the seconds in the units. So 24.5 radians per second. That is going to be the angular velocity at 0.3 seconds. Okay. So now the question is, what angle does the line PQ make with the axis at this time? Okay. This one, part B, is probably like the most difficult to visualize. Like you're reading that and you're like, okay, I want to know an angle, but can you imagine where this angle is on this picture? Are you able to visualize it? That's what I want to make sure. Oh, and I already drew on that. So let's go through that, since we are in a video and you're not in person and lecture with me, either live on Teams or in the actual lecture hall where I can show you this, right? This PQ, right, is going to spin around, and then it's going to move, you know, and like the weird part that's hard to visualize is that it could spin around like 3 or 4 times before it stops at a certain place, right? So let's say it stops right there, and this blue line is where it lands after 0.3 seconds. Then what the question is asking is, what is this angle? What is this angle here in teal? Okay. So, you know, when you think of it conceptually, I think that makes sense. And then now the equation that we're going to use is going to make sense, right? We're curious about position. Well, this is the position as a function of time equation, which is exactly what we need, right? We want to know the position at time t equals 0.3. So let's go ahead and write out what that is. Right, there's our skeleton equation. So now let's plug in everything we know. We're looking for this theta, right? This is at 0.3 seconds. This is at 0 seconds. This is at 0 seconds. This is the constant alpha. And then obviously t is going to be 0.3. So now let's plug everything in. Our initial angle was 0, right? We're starting off at 0 angle. Doesn't exactly say that anywhere, but we're starting to measure the angle at t equals 0, right? So in this guy right here, this is our PQ location. This is angle 0, isn't it, on an XY axis? So we are starting at 0. Our initial, our time, don't forget your negative. All right, I got 7.8 radians. So that's where the position is at time t equals 0.3 seconds. And so we're working, our answer's in radians, right? Because the units of all of our values are in radians, so our answer's in radians. And let's think about let's go back to our picture and understand where 7.8 radians is, right? Because we're not like super duper comfortable with radians. At least, you know, even to this day, I'm not like, I'll remember, you know, I remember obviously pi is 3.14, right? So if I look at 7.8, 3.14 is more than double that, right? 7.8 divided by 1 radian, which is 3.14. I mean, 1 pi radians, which is 3.14, is 2.48. So that means that this PQ line has rotated around 2.5 times roughly. So let me write out what I mean. So number of rotations. So what if this question asks you for the number of rotations, right? How many times did it rotate? Well, we know that the full rotation was 7.8 radians. We know that 1 full rotation is 2 pi radians. And so that means 1.24 revolutions or rotations, right? That's it. It went around one whole time and then stopped about a quarter of the way. Okay, so here's PQ. So we start the clock. Here it is at t equals 0. It starts rotating around, right? Rotating around. And it's going to rotate, do one complete rotation, and then it's going to go about a quarter of the way, and it's going to land right here. So the question is, what is this angle, right? What is that angle? What is the angle that the PQ makes with the x-axis at this time, right? So what we're really after is not the 7.8. The 7.8 is not, it's one answer, but it's not the answer to the exact question that was asked, right? The 7.8 is how far did it travel in 0.3 seconds. Now, what angle does it make with the x-axis? That is where we had to do this business here. So we have 1.24 rotations, which means we have 0.24 of a rotation that that it completes after crossing the x-axis. So, I should have written rotations. Okay, 0.24 rotations. If one rotation is 2 pi radians, then we can convert this to radians, right? It's a quarter of 2 pi, roughly a quarter. It's about 1.5 radians. 1.51 radians, and so 1.51 radians, how many degrees is that? We can figure that out. We divide by 2 pi, right? And it's about 86.56 degrees. So, which makes sense with our little analysis, right? That's almost 90 degrees. That's definitely almost a quarter of the way around the full circle. So, we've talked about a lot in this example here. Not only did we need our, kinematic, this was all kinematics, right? This was all chapter 2, 3 stuff, right? Kinematic with new terminology. Now, what's slightly newish is, being very comfortable with angular units and correctly interpreting what the theta equation is giving you versus what the question is actually asking, okay? The theta equation, there is no XY position dependence, right? It's only time. So we had to plug in the time, 0.3 seconds. And what we got out of that is how much total travel occurred over that period of time. But what part B wanted to know is, what does the angle make with the x-axis at this time, right? Which is not the full angle that was made during that 0.3 seconds. So the key idea here for these types of problems, and this is definitely an exam style problem, so I would review this and similar ones, okay? There'll be several of those on the exam. Key idea here is, right, these relationships between angular position, angular velocity, angular acceleration, they are all related the same way that the linear variables were. And so if you were really good at projectile motion, Or even if you weren't, now is the time to get good at it, right? Maybe things will click now because you're seeing it happen again in a different context, and then your brain kind of sees them both occurring and it's going to lock in at that point. We can only hope. So now let's get to the part of the story where we actually do connect back to linear motion, okay? We're going to connect them together. So now I want you to think of this object, a rotating object, all right? And in this case, we have a rotating blob, all right? It doesn't matter what it is, it's a blob, okay? It looks like this. And what we're going to do is we're going to pick one particular point on this rotating object and examine the motion of that point, okay? This point in the future is going to be the center of mass, right? But now it's just a point. But just thinking ahead, right? This point, how do we interpret an entire body as one point is, well, we put all of our vectors on the center of mass, right? Okay. So that's just cluing you in there. So we're going to look at this one point. There it is right there, right? And this point is moving in a circle. So its linear velocity vector is going to point tangent to the circle, right? Right. And that linear velocity vector, its direction is going to change, but its magnitude is not, right? Its magnitude is going to remain constant because we're dealing with constant acceleration, right? Because we're dealing with so at this point, a distance r away from the origin, okay, meaning it's going to have an xy coordinate as such. That means, okay, hold on. So now we're getting to the point where we're going to relate linear and angular kinematics. So the question is, if we're given rotational information, how do we find the linear speed and acceleration of a particular point on a rotating body? Okay, and so this is where we're going to compare our position in xy to the radius of the motion, to the angle that the object is making with the x-axis, all right? So this is a picture of our object. It's a, three-dimensional blob. We're going to select one point on that blob to measure, and that point is right here. And then we're going to build an XY coordinate system around that point such that the axis of rotation is at the origin, and then the point is obviously going to be located on that circle, right? So the first thing you might see here is that the linear velocity vector of point P is given, first of all, is the tangent, right, to the circle. So it's a vector that's tangent to the rotational motion. That is what tells you it's linear. And then that relationship is equal to r omega, okay? So where did that come from? Let's dig in, let's unpack. Well, let's look at the arc length of this point as it's connected to the x-axis, right? We're going to track that arc length s, and we know that that arc length s is equal to r theta, okay? So what s is actually doing for us is s is going to be the linear distance or the translational distance. I hesitate to use the word linear because obviously s is curved, right? But if S is small enough, it could be approximated as linear, right? If my S was just this little piece right here, under certain approximations, that could be a straight line. So anyway, what S is doing, S is kind of like our linear term, and the way it gets related to our angular position theta is through r theta, right? The definition of arc length. So we start off with that definition of arc length, and let's take the derivative of both sides. The ds dt is essentially our linear velocity, right? It's the change in this position, or I'm sorry, this change in this distance over time. And if we take the derivative of the right-hand side, well, r does not change with time, right? This p here is not shrinking or expanding out. And that's what we mean when we say rigid body. When we say rigid body, we mean that this point P, its relative distance from the origin does not change at all, right? This blobby thing is a rigid blob. It's like a rock, okay? Not a squishy, whatever, squishmallow. So r does not change with time, right? R is a constant, comes out of the derivative. What's left is d theta dt, which you and I have already decided is omega, right? So now you can see where v equals r omegas come from. There's like a lot of s's there. Where v equals r omega comes from. There we go. So v equals r omega, this is what you need to remember. This is the fundamental relationship that connects rotational motion and linear motion. So this is what you need to recall, and you can use it all the time. Use this all the time. Okay? So think back to this. Whenever you're doing a problem and you get stuck, think, oh, does v equals r omega help me? So we talked about how the linear velocity is related to the rotational motion. What about the linear acceleration? It's a tiny bit more complicated, because you might recall from earlier in this course that the acceleration of a rotating of an object moving in a circle, right? We briefly talked about that. That acceleration vector, it can point fully radially, or it could have a small component along the translational motion direction, okay? And so anyways, what I'm saying is that while the linear velocity vector only points in one direction, right, either pointing toward, the motion or behind, the acceleration vector can point, have an x and a y component, right? But we don't use x's and y's when we talk about rotational motion. We're going to use instead radial direction and tangential direction, okay? That way, those directions are constant no matter where that object is, right? And so what do I mean by that? If the object was over here, then its acceleration vector, let's say it's this guy right here, it's going to point like this, and you can see that its x and y component change, right? Its x and y component changes as it rotates around. It's not going to be the same as it is up there. But what doesn't change is how much points in the radial direction and how much points in the tangential direction. So we use those two orthogonal directions instead of x and y to describe the components of the acceleration. So let's break it down. So the tangential component is obviously the component of the acceleration that points along the velocity direction. And that is simply equal to r alpha. Okay, and then the centripetal or radial acceleration, that is equal to r omega squared, or v squared over r. Okay, and these are equivalent. You just make the substitution, v equals r omega, to get the other form. Okay, so now let's take a look at when you have a tangential component and when you have a radial. Well, you always have a radial component. So this is what I'll tell you right now. if there is rotational motion, you will always have a rad, right? A rad pops up because your X and your Y are changing directions. Not necessarily that V is changing, right? The magnitude of V doesn't need to change, but the direction that the velocity vector points, when it changes, which it must do when rotating, you're going to get a rad. But the only time you get a tan only appears when your linear velocity V is not constant, meaning your linear acceleration is not zero. So you have a tangential component only if the rotation is speeding up or slowing down. Okay? So this is just a quick reminder that, whenever you use radians, actually, let me rephrase that. Whenever you're doing math with angles, you need to use radians, okay? So if you are multiplying an angle by something, you have to use radians because radians are essentially unit because essentially the unit is the number 1, right? Meaning they are not units, right? A radian is not a unit. A radian is a ratio of two numbers that have the same dimension, right? A radian is S over R. What are the units of S? Meters, right? What are the units of R? Meters. So radian is essentially the number 1, right? And so therefore you can multiply anything by a radian and you don't mess anything up. However, degrees is a real unit, right? Degrees, when you multiply something by degrees, you are now changing the units to be meters degrees. Okay, so therefore you do not want to do that because that is not a real unit. In this example, we are exploring the two components of acceleration, okay? And this is a really good example that's going to help you solidify your fluency in angular acceleration, okay? So we have an athlete that whirls a discus around, okay? And they whirl it around in a circle of radius 80 centimeters. So there's the disc, okay? And here's the center of the disc. And then here is the guy's shoulder. And so when he spins around, he is essentially rotating this point about a circle of radius 80 centimeters, okay? So that's exactly what's pictured on the right in part B. And what we know is that at some moment in time that the athlete is rotating at 10 radians per second, okay? We don't know if that's positive or negative. That's a speed. And that the angular speed is increasing at 50 radians per second squared. So that's our alpha. So the question is, what are the tangential and centripetal components of the acceleration? And then what is the magnitude of the acceleration? We might be able to do all this here in this slide. So let's write down what our radial acceleration is. It's equal to v squared over r, and our tangential is r alpha. V squared over r is also equal, when I substitute v equals r omega, it becomes omega squared r. And just to verify, right, you can go back up here. There we go. So we need to find out what those values are. So we need to make sure that we carefully put the right quantity in. So A rad, working on A rad, it's V squared over R. Do we have V? We could find V if we wanted to, but we don't have V. What we do have is omega, so we might as well use that. So we have omega. And then we have our radius, right? 80.8 meters, right? Make sure you convert to meters. And we get 100 times 0.8, which is there we go. So what about the tangential component? That's easy. We can just multiply our acceleration, angular acceleration, by the radius. Oh, that's 50. And we get half of our earlier value, right? Because we're multiplying it by 50 instead of 100. So these are our components of the acceleration in the tangential and radial directions, okay? At that time, you know, depending on where you place the discus on the circle, you could do the same thing and find x and y, right? You would just need to know where the discus is in relation to the x-axis. So this is just, again, like I said before, right? When we describe rotational motion, we don't like to use x and y explicitly. We like to break the components into radial and tangential. So the final topic in rotational motion is energy. So we are kind of hopping around in the book. Essentially, we looked at projectile motion, right? But translated into rotational motion. Now we are looking at energy in terms of rotational motion. And then we will get to the Newton's laws aspect in chapter 10. Okay, so we're kind of like jumping around a little bit. So energy and rotational motion, right? It's all going to start with kinetic energy. So let's say we have an object made up of multiple masses. So here's kind of like a typical baton, right? A baton is a classic example. A baton is a stick with a ball on either end, okay? And this baton is twirling around. So each ball at the end of the baton is going to be a mass rotating, right? And so each one is going to have a kinetic energy equal to 1/2 mv squared. Sure, right? And then we are going to take that v and represent it as a rotational quantity using the connection of v equals r omega. So now we can turn that kinetic energy into one that is in terms of linear motion to one that is in terms of rotational motion. So we get 1/2 m r squared omega squared. So the total kinetic energy of this system with the two objects would be those two terms added together. Okay, great. We're on the same page. Now, what if we play with it a little bit? We play with that and we take out some common factors between the two objects, right? The common factor being a 1/2 omega squared, right? They both, M1 and M2, are traveling at omega squared because they have the same radius, right? So we pull that out, and everything that's left behind, which is mr squared, is going to be included in a summation, right? Because we're adding essentially mr squared for each object in the system. This mr squared is actually a term called the moment of inertia. So if you add up all of these mr squares for all the particles in your system, what you're actually calculating is the mass analog, okay, to a rotating object. Because the mass is not the only thing contributing to the kinetic energy. The distance that the object is from its axis of rotation is also contributing, right? Because V equals R omega. So now the mass aspect of kinetic energy has this extra term multiplied by it, which is simply the distance that the object is from the rotation axis, right? And it's squared because V equals R omega, and that V was squared, right? So now we have this moment of inertia, and so I've kind of like shown it to you in a mathy sense, okay? You can see where it fits in the equation for kinetic energy, right? So it fits in as the mass portion, essentially, of the kinetic energy, right? The velocity portion is now omega squared. The mass portion is now I, okay? So I is a mass analog that has units of kilograms times meters squared. So you can think of it as a mass, but it does, in linear motion, the mass only the mass matters in relation to the kinetic energy. In rotational motion, the mass distribution is what matters, right? It's the mass coupled with its relative location with respect to the origin, or wherever you put wherever the thing is rotating about, right? Typically we put the rotation axis at the origin. So now let's talk about conceptually, what is the moment of inertia? What is it? You have a good mathy idea of what it is, but what is it like physically and conceptually? This is an apparatus. I don't have it here with me at home. Maybe you can visualize what it is. So you have this kind of like double T-shaped bar, right? And you have these little masses on there that can be slid out and in. And so I want you to imagine rotating this object when the masses are pushed in close together. What that means and what that's going to feel like, if you're imagining it, is it's going to be relatively easy to start the apparatus to rotate, okay? The masses are close to the axis, meaning your quantity mr squared is small, right? Because r is small. It's a short distance away from the axis, right? R is small. R is the distance from the axis of rotation to the mass, right? So if the masses are real close to the axis of rotation, then your mr squared, or your I term, is going to be small. And if your I is small, right? If your I is small, well, then your K is small, right? Now, what if I push those masses out? Well, now my I is going to be big, right? I is going to be big because R is big and R is being squared, right? So that must mean that K is going to be big. And if K is big, that means that it's going to be harder to start the object to rotate, right? Because look how much kinetic energy it takes. It takes a bunch more than this version. So it's going to be harder to rotate. So that's going to give you a good conceptual idea of moment of inertia, okay, and what it means. It means essentially something with a high moment of inertia is difficult to rotate. Something with a low moment of inertia is easy to rotate. This is an example where you're going to be calculating the moment of inertia of this strange looking object, okay? And the thing about moment of inertia is it's axis dependent. I know I spelled dependent wrong. So what do I mean by axis dependent? Well, where, the axis of rotation, wherever you rotate the object, right, the R is going to change, okay? What I mean is that if we rotate this object about here, this A, so basically I'm grabbing, let's say I'm pinching this with my fingers, okay? I'm pinching this and I'm pinching this with my fingers, okay? There's my thumb and my fingers, I'm pinching it like that, and I'm allowing mass B and C to spin around in a circle, right? one after the other. That is going to give me a different moment of inertia than if instead my axis was right here. Okay, what if I'm holding on to this with my hand, with my claw, right? And then I'm allowing this guy A to rotate, okay? Right? This apparatus has if not more, moments of inertia, right? Because it has 2, if not more, places I could rotate it. So each place that I could rotate it is going to give me a different moment of inertia. Does that make sense? So now that I kind of broke that down for you, I want you to DIY this. Okay, definitely do this one. And understand every step, because this is definitely an exam type question. And then this slide is essentially reiterating what I had mentioned, my hints for this problem, right? Moment of inertia depends on the choice of axis, okay? In that problem, we were given 2 choices of axes, 1 through point A, like this, so that B and C are rotating around like that, and then 1 through BC, so that A is rotating like that. And notice how it didn't matter that A is rotating about an axis pointing up and down, and B and C are rotating about an axis coming out of the page, right? None of that matters. What matters is the mass and how far it is from the axis of rotation, okay? And you might need to do some Pythagorean theorem to figure out what that distance is. So there are many objects, many different types of objects that, standard objects that we have already calculated the moment of inertia, all right? And so these calculations have already been done. So these are ones that you can just memorize and reuse. So if you're dealing with a situation of a rod and the rod is rotating about its center, well then that moment of inertia is going to be 1/12 ml squared. And if you're dealing with a rod, but the rod is rotating about an end, well then its moment of inertia will be 1/3 ml squared. And so which one has the smaller moment of inertia? This guy, right? His moment of inertia is smaller. And the reason for that is it has more mass closer to the axis of rotation than this guy, right? There's only one set of masses that are super close to the axis of rotation for figure B. But for figure A, you have twice as much, right? Twice as much. And it's not linearly related. There's a square, right? So it's not going to translate to twice as much. It's not going to translate to twice as much moment of inertia. It's going to be actually 2 to the squared times as much, 4 times as much. And indeed, you can see that there is a factor of 4 relationship here in between those 2 moments of inertia. Other objects, plates, okay, depends on where the axis of rotation is. Cylinders, okay, a couple different types. A hollow cylinder where you have 2 radii. Hollow. A solid cylinder where you have obviously solid piece of metal or whatever it is. And then the thin-walled hollow cylinder where it's essentially, this is so thin that you can ignore it. And it's just a shell, okay, on the outside. And all of these, all of our rotation axes are only going to be along symmetry axes. And we're not going to be nothing crazy, right? It's not going to be a axis of rotation about the top piece of this cylinder, okay? And then finally you have the sphere. The sphere is going to be you're going to see that a lot in your problem, solid sphere or a hollow sphere, okay? So now here's an example where we can use moment of inertia to solve some problems and basically energy analysis to solve problems, okay? So we have a cable that's wrapped around this cylinder, so it's kind of like a hose reel, okay? There's a cable here, you can't see it. And then this cable extends out like this, okay? This cylinder is a solid cylinder. So we can go to our table and we can say, okay, and then it's rotating about its center. So let's go to our table and look for a solid cylinder, 1/2 mr squared. Now we know the moment of inertia of that object. We can go ahead and jot it down. We know its mass, 50 kilograms, its diameter, right? D/2 goes there for radius. And that it's rotating about some frictionless bearings, meaning there's no friction going on. Okay, and then the axis is stationary and horizontal, meaning the axis is not moving, right? This rotation axis right here is still. So imagine grabbing the end of this cable here and you're tugging on it with 9 newtons of force over a distance of 2 meters. Okay, it's turning, it's unwinding. There's nothing weird with the unwinding. There's no slipping, meaning, and basically what I want you to take away from this phrase without slipping is that basically V equals R omega, right? For every turn, for every omega, okay, I know that's not the vector omega, but just the illustration vector for omega. For every omega, you have a V that's equal to R omega. Do you see what I mean? Like it's not slipping around. Like you're not suddenly getting a huge jump, getting a rotation and getting a huge jump in like loose rope. So what do we need to know? Oh yeah, so then we're told some initial conditions. The cylinder is at rest initially. Okay, so what does that mean? Omega naught is 0. And then what we're looking for is its final angular speed, omega, and the final speed of the cable, V. Okay, so we're looking for omega and V. So let's chip away at this problem. So we have some information, and let's review the tools that we have to use to solve this problem. One of them is kinematic equations, okay? Okay, related to both linear motion and rotational motion. And then the other thing we have in our toolbox is conservation of energy, okay? And so we're gonna need both here. So let's see how far we can get with kinematic equations, since that's what we were just working with, all right? And so let's write down a few. So we know, obviously, if the acceleration is constant. And how do we know that it is? Well, because we have a constant force pulling on it, right? Constant force means constant acceleration, right? So we know that we have a constant angular acceleration as well. So that means that we can use our kinematic equation. So for angular velocity, that is omega naught plus alpha t. And for angular angle, angular position, we have omega naught t 1/2 alpha t squared. Let's get some other non-time dependent. Omega squared equals omega naught squared plus 2 alpha delta theta. And I think those three usually work for me. Let's see. So we want to find the final speed, right? So sure, final speed. Okay, great. We have two options here to find the final speed. We can use this guy, but we don't have any time information. We actually have distance information, don't we? We have distance and force. So if I were to solve for omega, I would definitely have omega naught at 0, but I don't know alpha, right? And I don't know how long it takes, the time it takes to unwind. So I really don't know, right? Can't really use it. What about position? Well, I don't really know the angular positions of anything, so that doesn't help either. So we're going to have to figure out something else. We might still need kinematic equations, but maybe we should go to conservation of energy. So conservation of energy. Total mechanical energy is conserved, right? And so we have two time points that we are interested in. Our initial one, which we know omega naught is 0. And then we have our final one, which is what we're looking for, that omega, right? And what we have here is in a mention of a force, don't we? A force over a distance. Does that sound familiar to you? That is a work, right? A force times a distance is work. So, and that's the work done by a pull force, right? Which is a non-conservative force. So here's our conservation of energy. This is going to be our force times our displacement, which is the pull force, and the 2 meters of pull. And this is a pull force, which means that the direction of the force and the direction of the motion are in the same direction. So this is going to be a positive work. Okay. And then we have our initial kinetic energy, which is 0 because omega naught is 0. And then we have our potential energy term due to gravity. There's no springs. And everything about this problem does not change. None of its y-axis changes, right? So this is going to be 0 as well. And then we're going to have our kinetic energy, which is going to be 1/2 I omega squared, right? This is the omega that we're looking for. This is going to be the speed at the end of the pull. And then for the same argument as before, we're not going to have any potential energy. We're going to just say that this guy is sitting at on y equals 0. So now you can see that the work that we do to linearly pull the rope off of the pulley or the cylinder is going to translate into rotational kinetic energy, right? So we're going to use conservation of energy here to find our omega. So we have 18 joules of energy from the pull is going to give that wheel or cylinder 1/2 I omega squared worth of rotational energy. So now we can find omega. So what is I? 1/2 mr squared, and then omega is our unknown. So let's plug in what is mr squared for that cylinder was 50 kilograms times a radius of 0.6 meters squared, right? Because the diameter was 0.12. Oh, so this is 0.06. So now we can solve for omega. All right, 20 radians per second. So that's our final angular speed. That can be translated into linear speed of the cable using V equals R omega. Oops. About 1.2 meters per second. So the idea here is that the rotational motion of the cylinder and the linear motion of the rope are related to each other. As long as that rope isn't slipping off of that cylinder, as long as it's not stretching or shrinking, then V equals R omega, right? And so the speed of the cylinder is going to be related to the speed of the hose or the rope through V equals R omega. This example, I'm going to skip entirely. It's essentially another conservation of energy problem, and it's all algebraic. So I would reserve it to do it if you have extra time. And so I wanted to just kind of share an interesting idea, okay, that you may not realize, because we are going to start talking about the center of mass very soon. So it's going to come up again. And so what I want to express to you is that now when you are doing the conservation of energy, okay, this U term for gravity is going to be the Y coordinate that you're going to be using to find U grav is going to be the center of mass in the Y coordinate direction, right? So this is a perfect example of